Conjugation, resonance, and dienes. So first off, what do we mean by conjugation? If you recall, we talked about acid-base conjugates way back when, and conjugation in that regard, or conjugates in that regard, had to do with pairs, acid-base pairs. Well, with dienes, we have something similar as well. So a diene is nothing more than a compound that has two double bonds, right? Two enes, two double bonds. So you see that here. In order for them to be conjugated, in other words, in order for them to be paired up, it needs to follow something like this: a double bond, single bond, double bond. Or you can also have something like this. This would be a conjugated carbocation, not a diene, but a conjugated carbocation. It's allylic, meaning this carbon is adjacent to an sp2 hybridized carbon. Of course, this carbon is also sp2 hybridized. And so when you have something adjacent to an sp2 hybridized carbon, we say that's allylic. Another example of something that's allylic, maybe something like this. So we have an allylic alkyl halide. Alright, so all it means now for them to be conjugated is a double bond, single bond, double bond, or a double bond, I guess it's, if you wish, single bond, but this is a carbocation. So what makes it special is because of the pi bonds. So they're showing all these pi bonds. The blue and the red here is one unhybridized p orbital. So these are the unhybridized p orbitals. If you hybridized p orbitals. If you need to, go back and review the orbital diagrams, but the overlap here above and below, that's one double bond. So that's, say, this double bond. Then we have a single bond, and now there's another double bond here. Okay, so here's a pi bond, here's a pi bond. So if we can number these carbons 1, 2, 3, 4, it would be carbon 1, 2, double bond. Between 2 and 3, it's a single bond, and then 3 and 4, this is a 3. Between 3 and 4, we have the other pi bond. So what makes this special is that these pi bonds can overlap. If you notice, okay, well, we overlap here, great, the double bond, but you can also have this overlap here between carbons 2 and 3, even though you don't see it. And that's what makes this special. You see something very similar with an allylic carbocation. So I've drawn in the sigma bonds here, and now we'll put in the unhybridized p orbitals for these two. We have bond overlap of these unhybridized p orbitals above and below the plane. All right, so that's the double bond here. This carbocation, if you remember carbocations, they're also sp2 hybridized. Right? So this guy is also sp2 hybridized. What that means is we have an unhybridized p orbital. Now it happens to be empty, there's no electrons in them, but again, you can get overlap this way as well. So in these conjugated systems, what you notice is it's sp2, 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 sp2 hybridized in a 1,3 diene, sp2, sp2, sp2 hybridized even in an allylic carbocation. Okay, so as I was saying, when you have overlap of these p orbitals, we can put a double bond in here. So it's double bond, single bond, double bond. These p orbitals can overlap. That spreads out the electron density and makes them more stable. So a conjugated diene, the simplest one, 1,3-butadiene. Not all dienes, of course, are conjugated. Here's 1,4-pentadiene. We refer to this as isolated because we have two sigma bonds. It's double bond, single bond, single bond. Right? So we do have unhybridized p orbitals like this, but they're isolated because this carbon is sp3 hybridized. In a conjugated system, all these atoms are carbon atoms are sp2 hybridized. In your in the original PowerPoint, it might be clearer to see than in this printout, but you can see when you have a 1,3-butadiene, this electronegative negativity area, this electron dense area, this red splotch is spread out over all 4 atoms. In an isolated diene, it's just here and here, so it doesn't get spread out, and it has lower, or this has higher energy, less stable. This has lower energy, more stable. It does not mean they're not reactive, however. We'll talk more about that later. So first thing here is let's practice, find out if these guys are conjugated or not. Hopefully this printout is good enough for you to see. Let me just fix it a little bit. So here we have a conjugated diene, double bond, single bond, double bond. So yes. This is not double bond, single, 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 double. Right? So no, clearly not. This is conjugated. Double bond, single bond, double bond. So yes. This one is not. Double bond, single, single, right? This guy here, sp3 hybridized. So no, not conjugated. Talked about allylic carbocations as well. Allylic carbocations are also especially stable. Here we see, here's the double bond. Here's the, no, here's the double bond. Sorry. Guess double bonds are shorter than single bonds, so they illustrate that here. Double bond is shorter than the single bond. So here's the unhybridized p orbital of the carbocation. So let me just kind of put this in here like this. This has a plus charge, but that electron density then from this pi bond bleeds into the unhybridized p orbital of the carbocation. And again, if you're unfamiliar with what I'm talking about with unhybridized p orbitals, go back, I think it was chapter 2 or 3 where we first started talking about that in Organic Chemistry 1. So these carbocations are more stable, lowers the electron density, and if you remember with regard to carbocation stability, primary was less stable than secondary, secondary was less stable than tertiary. Allylic are even more stable, and we talked about this with regard to E1 and SN1 reactions, right, where we formed a carbocation. Carbocations were formed when the leaving group on that alpha carbon was either secondary or tertiary, but allylic as well. So we could have a secondary alkyl halide, a tertiary alkyl halide, right? So here's the leaving group. Allylic. This is even more reactive than the tertiary. More practice. Is this conjugated or not? Well, let's see. Double bond, single bond, double bond, single bond, double bond. Yes. sp2, 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 sp2. Is this sp2, sp2? Yeah, this is. Now it doesn't have to be to a carbon. These are all sp2 hybridized carbons. So, yes. Double bond, single, single. No, this guy's sp3 hybridized. So, no. Double bond, single bond. This is a carbocation. So let me put hydrogen out here. In a carbocation, if you recall, it has just 3 bonds. It's trigonal planar. just as what you'd have here with these alkenes, and we have an unhybridized p orbital that is empty. Right? So double bond single carbocation. So these now are all sp2 hybridized carbons. So yes. Is this? Well, double bond single single. No, this guy here is sp3 hybridized. So no, it is not conjugated. Resonance. We talked about resonance again back in Organic Chemistry 1. Remember, in resonance, what we're doing is we're moving bonds or electrons. So it's electrons that are moving. The atoms themselves stay put. So what we can do here with an allylic carbocation is we can move this pair of electrons over, so the double bond is here now. This carbon used to have a double bond. It still has two hydrogens. Remember that atoms don't move. It still only has two hydrogens plus a third bond to this carbon, right? So we're just moving the pi electrons, not the sigma. So the sigma bond stays. So this carbon now has three bonds to it with an empty p orbital, so the carbocation kind of leapfrogs over, ends up over here. And this is resonating, if you wish, like a plucked guitar string. It's going back and forth, and so we can envision it as these electrons being delocalized and being in all positions at the same time. This is again what I was referring to with regard to carbocation stability. Methyl carbocations don't even exist in this primary, secondary, tertiary. They put the allylic carbocation here, but if you notice, the reason for that is this is a primary allylic carbocation. It has two hydrogens. But what if we had a secondary secondary, make this a hydrogen, a secondary allylic, right? So this is a secondary carbon allylic. It would be more stable. This is a primary allylic. It has a one carbon-carbon bond, two carbon-carbon bonds. It's secondary. Secondary allylic is more stable than tertiary, and you could even have a tertiary allylic if you wanted. All right. A tertiary allylic would be even more stable. All right, now for a little review of resonance.